to this computer. Okay, there, that's what I wanted to hear. All right, so let's share. And as has been the problem for a while, I cannot put the slides in the Mathematica, so we're going to be jumping back and forth between the two. So let's take a look at the slides to start with, and then I will need to do where the heck is view and enter full screen. Okay, everybody can see the slides?
Yep.
Yep.
Okay, so this is a review of the material that we've done before. And I have some new added material about hypergeometric functions. And then I had hoped also to get Pade approximations, but I only got that very lightly started at the end, so we'll do that next lecture. Okay, come on. Page down, there we go. So we're going to have a quote as always, then we're going to start in the perturbation review, the way in which we do things, hard problems versus easy problems. We're going to learn about the hypergeometric series and then the generalized hypergeometric function and the generalization of the generalized hypergeometric function known as the Meyer-G function. And then we'll take a look at the hard problem that we were doing, look at a convergence series. We'll look at a different hard problem and do it all again. We'll learn about the online encyclopedia of integer sequences, and I wanted to do Pade approximation, but we are only going to get a very early start on that. Okay. So I love everything that Einstein always seems to talk about. Look deep into nature and you will understand everything better. All right. So we're doing mathematical physics, and there are various styles of doing mathematical physics. One style is very rigorous. If it's very rigorous, it'll be theorem and proof. I have never liked theorem and proof, and I find that much less interesting. I could even say I don't like theorem and proof type approaches. I prefer to use what I think is really useful and powerful mathematics techniques. Unfortunately, a lot of them are not rigorous. They will get solutions, but nobody knows why. Yeah, hi, buddy. Because of that truth, they are, of course, much more powerful when they work. Unfortunately, they're not always work. They don't always work, but they seem to work an awful lot more times than they don't. So the reason that I prefer less rigorous is that if you are more rigorous, you'll be less general. So that will mean you can't solve many new problems. Hi, buddy. Excuse me. Okay. Now, in most of the work that you've done previously or looked at, all school lectures tend to try to solve things exactly. And that's very nice when you have a problem that you can solve exactly. But usually there's about maybe 3 or 4 exactly solvable problems. And those have already been solved long ago. So the rest of all the interesting problems that you need to be solved can't be solved exactly. And as far as I can tell, there's basically 2 approaches. Either you can use numerical methods, which I use all the time, but this is not a course on numerical methods. So even though I trust them and use them, we're going to talk about a more analytical approach to very hard problems. And for that, there's really only one approach, and that's called perturbation theory. Yeah, I kid. All right. So, how does perturbation theory work? Well, you got a hard problem, and you have to insert a small parameter, epsilon. Then you expand the answer for the hard problem as a series in powers of epsilon. So the answer is you have a polynomial sum n equals 0 to m an epsilon to the n, and you take the limit as m goes to infinity. When you're all done, then you set epsilon equal to 1 and sum the series. This, unfortunately, is not easy. So we're going to, first of all, just do the easy part, which is finding the A's, and then we're going to start talking about summing the series, which almost uniformly are divergent. That is, they sum to infinity. Now, the 2 answers we're going to look at turns out to be convergent, but that's really, really unusual. And for the second one that we're going to do, doesn't matter. The radius of convergence is about 0.08 something. So you're not even close to 1 in that one. So, however, let's move on. Okay, so now we're going to stop the share and let's, where's my, of course you're going to move this. Oh, God damn it. Zoom keeps doing things that drive me crazy. All right. Thank goodness. All right. I apologize. This stuff just drives me crazy. All right. I'm gonna hide the caption. Well, I wish they would let me move it somewhere else. Oh, they can. Thank goodness. All right. Now we're going to share Mathematica. Okay. So hopefully everybody can see Mathematica.
Yes.
All right. So we're going to take a look at a problem, the simple fifth degree polynomial, x to the fifth plus x equals 1, which of course, first of all, it can be factored. So 1 minus x plus x squared times minus 1 times x squared plus x cubed. And it has some exact solutions here. So and we can take a look at the numerical values. So there's one real and two complex conjugate pairs, which is what you're always going to get. Whenever you get a complex result, you're going to get a complex conjugate pair. Okay. So Mathematica knows exactly how to solve this. So it's 1 minus epsilon over 5 plus epsilon squared over 25 minus epsilon cubed on 125, ... So this is what we want to find, how to get these coefficients, 1 over 5, 1 over 25, etc. Okay. So we're going to use the perturbation theory. And the first thing you do is insert a small parameter, epsilon. Of course, where should you put it? There's at least 2 and maybe 3 places that you could put it. You could put it in front of the 1, but if you did when when epsilon goes to 0, the solution is 0, and the series is going to start with the constant 2. So 2 is not equal to 0, and that's not usable. So we couldn't put it in front of that term. So let's do it in front of the x term. So the first step in the process is to solve the easy problem. So if epsilon goes to 0, this is going to be x to the 5th equals 1. So I can solve all of those things, and they're 1 minus 0.8 plus minus 0.6 I, etc. Now, just to notice, the first solution is 1, and the exact solution is 0.755. So that's about a 30% error. And when I was doing astronomy in graduate school, we would have error sizes of a couple 100%, sometimes thousands of percent. So that's a pretty good first approximation right there, at least compared to what we did in astronomy. So the next step, everybody understands what the first step is? Any questions about that? Okay. The next step is to use the ansatz. So we're going to have a series, which we're going to be 1 plus a series of coefficients sub n. N goes from 1 to m, epsilon to the n. So for 4 terms, the example is 1 plus a, where I used a for the variable up here. So we have 1 plus A1 epsilon plus A2 epsilon squared plus A3 epsilon cubed, etc. So that's the ansatz that's always used in perturbation theory. Everybody know about the ansatz? Anybody not know it?
You can go over it again.
Well, the ansatz is that there's going to be an infinite series that you can compute. You have 1 plus some unknown coefficient A1 times epsilon plus a second unknown coefficient A2 times epsilon squared plus ... Goes off to infinity. That's the ansatz, that you're going to assume that everything can be written in terms of the small parameter that you've used before. And the first one, is the solution that we had from the easy problem, setting epsilon equal to 0, we got 1. So 1 plus all of the rest of the stuff that we don't know. We don't know A1, A2, ... So the next thing you have to do is substitute that ansatz into the hard problem. Okay. So we have S of epsilon, and we're doing 3 terms right here. And so that series goes to the 5th power plus epsilon times the x, or the ansatz S of epsilon. So that's our hard problem. And in order to do the Taylor series of something in Mathematica, it's called series. And we're doing it in around epsilon from 0 to 3 terms. So we're going to get a solution, which is order of epsilon to the 4th. So we get 1 plus 5 A1 epsilon, A1 plus 10 A1 squared plus 5 A2 epsilon squared plus 10, etc. epsilon cubed. So when you're doing this, you need to do approximations for these higher powers. And usually you can use the binomial theorem to approximate these for a few terms and not have to do everything multiplied out the hard way. Okay. So I write my hard problem. X to the 5th plus epsilon x is equal to 1 plus 0 plus 0 plus 0 plus an infinite number of zeros. Why do I do that? Well, we've got a series on this side, for the left side, and we need a right side series. And we want each term to be the same. So the 1 is going to be equal to the 1, and the 1 plus 5A1 is going to be equal to 0. And the second one is going to be equal to 0, and the third one is equal to 0. And you can do that as much as you want. So I can create my right-hand side as a list 1, 0, 0, 0. Then I can take my polynomial up here, to take a Taylor series and make it a polynomial, you use the normal function in Mathematica. So we had this function up here, ascent 3, which is this fourth order Taylor series. So we take the normal of that, which makes it a polynomial, and then we get the coefficient list of all of the epsilons. And they're the ones that we had up here. 1 plus 5 a1 plus 10 a1 squared, 5 a1, etc. Okay, so we can take our list of ones, set it equal to these coefficients, and make them equal to each other. So 1 equals 1 is true, and 0 equals 1 plus 5a1. If you know a1, the second one tells you 0 equals a1 plus 10a1 squared plus 5a2. So you substitute in a1 and you get another linear equation. And then if you know a1 and a2, you can substitute in this and you'll get another linear equation in a3. And you'll notice that our hard problem has turned out to be an infinite series of linear equations. Very easy. Same thing you could have done in 7th grade. So we've changed our hard problem into a 7th grade problem. Okay. So I can use a for loop to iteratively solve each of these equations. And I have a list of coefficient results. So for I equals 1 to the length of the number of equations, keep adding 1 to itself. Take each equation, solve it for an appropriate a sub I. And so I'm starting here from I equals 2, so we need to get the first one, I minus 1, a sub I minus 1. Then append to our list the solution of this. Happens to be that solve always gives you a list of depth 2. So I need to get rid of those lists, and that nest first solve 2. That just gets rid of those lists. So I append the solution, and to CF, go back and do it again. But the first time I had no solutions, but the second time I have a 1. So I can solve the second equation substituting the a1 equation, and then solve that to get a2. Do it again to CF. Now I'll have an a1 and an a2, and I keep going around doing that until I've got all of the solutions to my equations. When I do that, I get minus 1/5, minus 1/25, minus 1/125. Okay, so that's the basic process that we do. Everybody understands how we do perturbation theory. We take a really hard problem and we make it a very easy, sequence, an infinite sequence of really easy problems, 7th grade problems. Okay. So now I can take all of the code that I've done from the beginning and write some code to do this for an arbitrary number of coefficients. And so if I want to do 15 terms and I'm going to use my ansatz S, I'm going to use the variables as a sub I and epsilon for my small parameter. All of that is, all of the things that we've done previously have been put into this single bit of code. So I run it and I get minus 1/5, minus 1/25, minus 1/125, 0, 21 over 15, 625, 78 over 78,000 something, etc. So this looks like it's convergence, and as we'll see, it actually is convergent. So this is one of the few times when you can actually get a solution. There's, of course, the first question you have to ask yourself is, since I can't run a computer for an infinite amount of time to get an infinite number of solutions, I have to find an approximation or have to understand how this series of numbers are. And the only way that I know about it are two things, which we'll take a look at. And the first one is simply stare at them and try to figure out what the heck is this sequence. There's got to be a recurrence equation somewhere. At least we hope there is. And we're going to find out that if you do stare at it long enough, you actually can find that. Okay. So let me stop the share. And then we're going to go back to the slides. Everybody know what we were doing there? Everybody follow that? Where's my... I had a slide here. This always annoys me. Okay. Let's go to that. Oh, that's why that's a problem. Okay. I had it in full screen mode, and that always screws up Zoom. So now if I share it, I can go back and get it. And now I can go back to full screen, and we've gone to MA. Whoops, where are we here? Okay. All right. So if you haven't been able to figure out what the general terms are, it turns out that if you stare this long enough, you'll see that each of the ends is minus the gamma function of 4n minus 1 over 5 divided by 5 times gamma of 4 minus n over 5 times gamma of n plus 1. Not always easy to see these things, but anyway. So if we take these coefficients and sum them for increasing n, they would be the series as at epsilon equals 1. So what do I get? Well, it's definitely not monotonic. So in fact, it's not even monotone non-decreasing. Goes down for a while, even because there's a 0, then it keeps going down, then it goes up again, finally a little bit lower, keeps going down, goes up. So you don't even know necessarily, if you're doing this numerically, how many terms you should add, because sometimes the error would get worse. But at least it is getting better. I mean, the relative error from the solution to compared to the real one keeps going down. You just don't know how many terms, and sometimes you're going to get worse before you get better again. So that's one of the problems with perturbation theory. It would be nice if it was monotone or non-decreasing monotone, but it isn't even that. So I want to sum the series. Here's our ansatz, and now we know the actual coefficients, so we can take the sum from n equals 0 to infinity with epsilon. Now, in the 1950s and 1960s, there were two breakthroughs in Mathematica. Not in Mathematica, in mathematics. One was an algorithm for solving sums. And there is an actual algorithm for computing the sum for any infinite series. That used not to be before 1950. Everybody just would have to go to look at Ramanujan's notebooks and find a series that he'd figured out what was the right answer. So there were all of these books of tables of sums, and you'd spend your time going through the pages trying to figure out what one had a solution. Finally, in the 1950 and 1960s, they figured out how to do the sums automatically. And then in the 60s and 70s, they did the same thing for integration. So we now have two algorithms for computing infinite sums, and mostly for integrals that have limits. Okay. So what do we have for the solution of this? Because this actually does have a solution. And it turns out that it's a hypergeometric series, actually a sum of various hypergeometric series. And hypergeometric series are something that were first looked at by Gauss and Euler in the 17 and early 1800s. So, and they turn out to be very useful. And as I said, people have worked on these over the years, and they've generalized the hypergeometric series, and then they generalized the generalized hypergeometric series. So we're going to go a little short review of those kinds of results. So the hypergeometric function is a solution of a differential equation, which is not a constant coefficients. So here we have z times 1 minus z y double prime plus c minus a plus b plus 1 z times y prime minus AB y. There's three in the original hypergeometric function. There are three unknown constants A, B, and C. So in order to solve this, we use the Frobenius method, and we wind up getting a series that looks like this. And obviously, since this is equal to 0 plus 0 plus 0 plus 0, an infinite number of zeros, each of these coefficients is equal to 0. So we can get a recurrence relationship for a sub n plus 1 in terms of a sub n. And assuming, that this series has a solution an z to the n, then you get a solution 1 plus ab over 1 factorial c z, a times a plus 1, b times b plus 1, 2 factorial c times c plus 1 squared plus ... And there's a way to write that. You've probably not heard about the Puck-Hammer symbol, a sub n and b sub n and c sub n. So this is the so-called regular solution. It has no singular points in it. And so you can write it this way. It's the same series, and it'll converge whenever either z is equal to 0 or the real part of c is greater than 0, or c is not an integer and z is not equal to 1, or the real part of c minus a plus minus the quantity a plus b is greater than 0. So these are the convergence rules, and the a sub n is what's called a Puck-Hammer symbol, and a sub n is a times a plus 1 ... a plus n minus 1, which, if you think about it, since gammas are basically factorials, we have gamma of a plus n divided by gamma of a. Okay. So there is another solution which has a singular point at 0. You have a sub 1, a 2f1. This is the regular solution. And then you multiply z to the 1 minus c, which is a singular point since c is greater than 1, and times a different regular one, a plus 1 minus c, etc., times c. So this is the complete solution to the hypergeometric function. You can take the derivatives of these, and it turns out that the derivative is got some relatively straightforward coefficients, and you add ones in various places, things like that for the first derivative. Second derivative gives you the same thing, but you have a plus 2, b plus 2, c plus 2. And there's a whole bunch more, which in the bibliography, the 20th one, page 8, has a whole list of these things. So you can use the hypergeometric function with special arguments to reduce to various elementary functions. So 2f1, 1, 1, 1 turns out to be just 1 over 1 minus z. So the binomial 2f1, 1, 1, 2 turns out to be minus the log of 1 minus z over z. And 1, 2, 1 is 1 over 1 minus z squared. And 1, 2, 2 turns out to be the same as 1, 1, 1. That is what we looked at here, 1 over 1 minus z. So many of these hypergeometric functions turn out to have elementary functions for solutions. You can also write it as an integral. And these are very useful for using asymptotic approximations to hypergeometric functions, because we did a lot of work of getting various integrals of, I think I screwed up in here. Yeah. This is part of the exponent. So t to the b minus 1, and this is t c minus b minus 1. These are the exponents, not coefficients. So I screwed up the typing on this. I apologize. Anyway, so you can write the same function as an integral from 0 to 1. This was first shown by Euler in 1748. And in 1908, Barnes gave a contour integral from minus I infinity to I infinity. And you've got these various gammas here and integrating over S. If you remember from complex variables that we did about 3 years ago, these are pretty straightforward using the Cauchy equations. Okay, however, of course, there's always limitations. The argument of z, minus z, has to be always less than pi. So you can't have a negative value, because the argument of minus minus would be a plus, and it's got to be if z is positive, this will be minus, which would be pi in the complex plane. So you can't have a positive z. And the path is curved in this integral if necessary, because there's a whole bunch of poles whenever s is equal to minus a minus n, s is equal to minus b minus n for all n. And this was shown in Whittaker and Watson, which was around 1900, but the version that I have is from 1990, a reprinted version. So there's been a long history of mathematicians who have determined the properties and generalizations of the hypergeometric function. And George Arfken, Arthur Edley. Edley was a student of Hardy, and he did a lot of really interesting work. The original hypergeometric function was from Gauss and Euler. Many of these other people generalized the hypergeometric function, and the most important one was Cornelius Simon Meyer, who generalized the generalized hypergeometric function. And he did it because he was trying to show that all special functions in mathematical physics could be written as a hypergeometric function, a generalized hypergeometric function. So he found a particular generalization of it that allows you to do that. So this group of people are the people I call murderers row. They're the ones who have done most of the work in this area, but not complete by any stretch of the imagination. There's a whole long industry of people who have been doing this since the 1800s. Okay. There's many, many properties of the hypergeometric function. You can find recurrence relationships. So if you know one value at some particular value of, A, B, and C, then you can find, suppose C is C plus 1. Then you can get a recurrence relation in terms of the previous value. And sometimes you need 2. So there's all these recurrence relationships. Everything has always got an integral formula. You can always write one of these things as an integral. Turns out they're very useful in integral transforms, Fourier transforms, Laplace transforms, Mellon transforms, Barnes, Euler transforms, Wimp, Narain, Meyer, you name some integral transform, which is very useful, is usually can be very nicely written in, can be done for any of the generalized hypergeometric functions. There are various multiplication theorems. That is, you can take a couple of hypergeometric functions and multiply them, and you'll find out that they give you a different hypergeometric functions. You can do continued fractions. You can do derivatives. You can do all the things that mathematicians want to do. So let's go a quick review of the generalized hypergeometric function. And instead of either 0, 0, 1, 1, 1, 0, 0, 1, or 2, 1, which are all the ones for the hypergeometric function, these are, you have 2 lists of constants, and there are P of them, A1 through AP, and Q of the other, B1 through BQ. And again, this is all written in terms of the Pochhammer coefficients, A sub n to A sub P sub n, and the B's Z to the n over n factorial. Now, not everything always has a defined coefficient here. But if it is non-zero for all n, then the generalized hypergeometric function has a non-zero radius of convergence. By the way, is everybody following me? Any questions at this stuff? Nobody seems to be talking about anything. Okay. So, and if it does have a non-zero radius of convergence, then the series defines an analytic function over some region, and you can analytically continue it afterwards. So you will get an analytic function out of it. Now, all of these parameters can be changed without changing the value, the actual elementary function. For instance, 2f1311 is the same as 21131 is the same as 103 is 1 over 1 minus z cubed. So there's all these various coefficient constants which will cancel out under various conditions. So the choice of parameterization is not always unique. Everybody clear about that? And as I said, many of the special functions, the earth, the ERPhi, the Airy function, you name it, Bessel functions, etc., turned out to be solutions of the generalized hypergeometric function. And people wanted to determine all of the special functions. And C.S. Meyer, he was the mathematician that created this particular generalization of the generalized hypergeometric function, which is called the Meyer G function. Everything was always an F, so he added to the next letter to the G function. So this is Cornelius Simon Meyer. And this is, again, you can do it in many different ways. This one is the integral form. So you can do a line integral in the complex plane. And you have to be careful because there's all kinds of poles and you have to go around the poles. It's a complex line integral, but everybody eventually figured out how to do it. And so you've got this integral as a certain type known as a Mellon-Barnes type. You can think of it as an inverse Mellon transform, whatever you want to do. There's all kinds of assumptions that you have to make about M and N and Q and P and what various A's and B's are not equal to, and whether any of various poles of the gamma function coincide, and on and on. So it's a hard problem to work analytically, but Meyer did it and came up with this function, which turned out to be able to represent every special function in mathematical physics. Now, there are some historical reasons that the lower, if you notice, there is QBs and PAs. These are in the lower. And then there is various products in the integral that are m's and n's, and it's historical reasons that it's mn at the top and pq at the bottom. There's no particular reason for that except the way it was done originally and the way everybody's followed to do it. Okay, so here's a small table of many of the types of special functions. What time have we got? Oh, all right. It's time for a break. So I'll stop here for the moment, and we'll take a 5-minute break, and then we'll continue. Everybody okay with that?
Sure.
All right. See you back at 11:07. Then we're going to share, and we're going to go back to the slides, and then we're going to view that in full screen, and everybody should be able to see the
Yes.
okay, good. All right, so this is not a complete list. This is simply one of the ones that are usually most used, Bessel functions, elliptic integrals, factorials, uh, all of the trigonometric and hyperbolic uh, trigonometric functions, parabolic cylinder functions, all kinds of stuff that are usually used. So just we're not going to go through an example of each of these, but I do want to show a few examples in the Meyer G. Okay, let's put that in. Okay, so the Airy function is the Meyer G with only one parameter, actually two parameters, but we have here, so that's one way you can get an Airy function. Here's a sine over the square root of z. That's a different Meyer G with two parameters here. Then we have an exponential divided by a square root of z, and you've got, again, a different parameter here. And then there's a k Bessel function, which you can write that way. And then here's the ERF function written as Meyer G, the ERF I as a complex version of the Meyer G, the exponential, the normal, e to the minus z squared, sinh, cosh. This is the fifth Hermite polynomial, which you can write as a sum of various Meyer G's. This is a parabolic cylinder function, d5, which again are sum of three terms. This is a polylogarithmic function written in a Meyer G. This is a Haver sine and an inverse sine, arc sine. So all of these can be written. And of course, the Meyer G, as I said, the reason that Meyer did it was to be able to show that you could write every special function in a particular hypergeometric generalization, which is called the Meyer G. As opposed, I don't know why they don't just call it the G. That's all he put in his papers, but everybody always calls it the Meyer G now. Okay. All right. So there's many, many, many examples. I could go on forever. That wouldn't help us with anything. But
Bob,
what?
is this just academic, or do you actually calculate these functions using the Meyer G
Oh, you
formulation?
compute them all the time. Yes.
But the question is there might be hidden zeros divided by zeros and all kinds of things you have to sort out.
Right. And you have to have that in the algorithm for computing this stuff. All of that stuff has to be in there.
Yeah, but I mean, in practicality, like say for a Bessel function, you just calculate the Bessel function, the formulas for Bessel functions or sines and cosines. I mean,
Well, most of the time, if there is such a special function, you'll usually find that the Meyer G, calls a particular special function if
yeah,
it's got the right coefficients.
okay, that's what happens. Okay,
Yeah, yeah.
okay,
All right.
thanks.
So why have I been wasting your time doing all of this stuff? Why do I care? Well, remember we were doing a perturbation series, and I said that it looked like it was a convergent series. And in point of fact, it is a convergent series. So here is the analytic function, the ansatz that we have for our perturbation theory. And we've got the gammas on as the ratio of these times epsilon to the j, and j goes from 0 to infinity. Well, as I said, there's an algorithm that was done in the 1950s and 60s, which will tell you how to compute this sum. And when you do that, you get this. So you get a series of 4 generalized geometric series or functions, and various epsilons to various powers of these things. Now, it's got a radius of convergence, which is 5/4, 1.25 times 2 to the 2/5, which turns out to be about 1.65. So the series that we computed has a real solution, and you can it is a convergent series, and the radius of convergence is greater than 1, so you can stick epsilon equals 1 into these things and compute the result just to see that it's exactly the same as the exact solutions. I took 5,000 digits of the exact solution and 5,000 digits of this series solution at epsilon equals 1, and they were identical. So this really is a solution, or this is the solution of our ansatz, of our perturbation series. So you can write a closed form solution for this because of the fact that it's a convergent series and the radius of convergence is greater than 1. Amazing. At least it's amazing to me. So, okay. Just to take a look at what happens here, this is the solution in terms of the generalized hypergeometric functions. This is the convergence radius, 1.65. This is our solution at 1, and we, like I said, the 5,000 digits, they're identical. So I assume if we did it for more digits, it would still be identical. Once you go past the radius of convergence, you have to use analytic continuation in order to get the rest of the solution. And that goes here. So we've got a solution here. So we've got this x to the 5th plus epsilon x equals 1, and at x equals 1, we get the right solution. Now you can do this all again using, when we did it, there were 5 solutions for 2 pairs of complex conjugate pairs. You can start each one of these with each one of the other ones, do it again, and you'll find out that there's also another hypergeometric function solution for each one of those. So in this particular case, when epsilon is in front of the x, all of this always works analytically. That to me is amazing because they almost never work. Okay. So let's take a look at a different hard problem. So we have our fifth order polynomial, x to the fifth plus x equals 1. And we put our small parameter epsilon in front of the x term. We showed that you couldn't put it in front of the 1 term. That got 2 equals 0, which is not true. So one of the other places we could have put it is in front of the x to the fifth term. Has anyone taken a quantum field theory course with perturbation expansions? Okay. Well, if you have taken one, you'll see that putting the small parameter in front of the x term is usually called the strong coupling expansion. And you can putting it in front of the x to the fifth term is called the weak coupling expansion. So here's a field equation, a scalar field, of course. I'm not going to take either vector or spinor ones. They're much more complex, and I'm not going to deal with that. But if you put it in front of the m squared, that's the weak coupling. I'm sorry, that's the strong coupling. If you put it in front of the side of the 4, that's the weak coupling. So we're using epsilon x to the fifth plus x equals 1 as our new hard problem. And we want to solve this using perturbation theory. Now, this might look innocuous, but it's not. It actually is quite violent. When we are letting epsilon equal 0, the x to the fifth term vanishes, and therefore 4 of the complex roots of the equation also vanish. And this intervention drastically changes the underlying structure of the problem, which you'll see shortly. Okay, so we're not going to do the calculations by hand. We're going to indulge ourselves with Mathematica. But first, let's take a look at the roots of the trajectory of our first, where we had epsilon in front of x. Okay. And we do our roots as a function of epsilon goes from 0 to 1. So they all start out here. And as epsilon goes to 1, they come into the results that we want. So they're always fairly close in this solution. So this is the strong coupling complex solutions as a function of epsilon, as epsilon goes from 0 to 1. The white dots are the solutions that we're actually trying to compute. So let's take a look. In the weak coupling solution, we notice that 4 of the 5 roots have vanished. And once epsilon is greater than 0, we have 5 roots. So we're only going to be able to solve for the real root, because you're going to get, you have, this goes to 0, so this is x equals 1. It's a real value. So you're only going to be able to get the real solution in this equation. So let me close this, stop the share, and let's share the Mathematica. Oh, I didn't do it. Damn. Sorry. I was supposed to change to a different code. Let me, what's going on here? Oh, I don't want to share. That's what's happening. Okay. Zoom is, of course, save. Come on. Everybody's stopped not seeing the share. Is that accurate?
Yes.
Come on. Drives me crazy when it is copying stuff into disk and it takes its sweet time. All right. So let me go into Mathematica and open. That. Okay. Let's evaluate the initialization cells. Okay. Now I can go back to Zoom and share, and hopefully everybody sees our new bunch of Mathematica.
Yeah, we see it.
Okay. So our hard problem is epsilon x to the fifth plus x equals 1, which for epsilon equals 0 has the solution a0 equals 1, the same one that we had before. So we're going to have our function, which is got a parameter e instead of epsilon, x to the fifth plus x. We've got a function of tables for our ansatz and a sub k. So our ansatz is the same as it was before, the sum of the variables times e to the k for the number of variables that we've put in. We take f, this function, put in the ansatz, take the Taylor series out to the number of terms, get the coefficients, set them equal to, get each coefficient equal to 0, solve each one, and those are going to be the solutions. And then we're going to have a function which will take all of the solutions and put them into the ansatz for any particular epsilon. So let's make that function. Oh, all right. So here is, we use E and we get 1 minus E plus 5E squared minus 35 E to the third plus 285 E to the fourth minus 2,530 times E to the fifth, etc. And out here at the 15th term, we got 3, 6, 9, 12. So 37 times 10 to the 12th. Obviously, it looks like it's definitely getting divergent. So if we took a look at all of the various values of G, we'd see that the sum is 1, 0, 5, minus 30, 255, minus 2,275, yada, yada, yada. So it is bouncing back and forth and getting larger and larger, clearly divergent, or at least you'd think so. Okay. So these are the first terms, and if I sum them, which I would do if I were doing one, we get the same result that we had up here. So that's just two different ways to do the same thing. Now, has anybody ever heard about the OEIS? Okay, so let me stop the share and go back to the Zoom, and we're going to share our slides. Okay, and now we're going to put it in full screen, and we're going to go to the next thing. The OEIS is the Online Encyclopedia of Integer Sequences. This was originally done at AT&T Bell Labs, and eventually Bell Labs went to whatever the New York Bell system was, and it just went to hell after that. So they eventually set up a foundation, and it's now a foundation. So what it is an online encyclopedia of integer sequences, and it was started by Neil Sloan while he was at AT&T Labs, and he transferred all of the intellectual property and hosting of the OEIS to a foundation in 2009, and is, as far as I know, still its chairman. So it records the information on integer sequences of interest to both professional and amateur mathematicians, and is widely cited. So as of February 2024, it contained over 370,000 sequences and is growing by approximately 30 entries every day. So, yeah, hi kid. Yeah. How you doing? How you doing, buddy? Okay, let me continue to teach. Okay. Yeah, I know you want to be petted. All right. So if you go to the OEIS website and you stick in various numbers, we have the ones that we had from before: 1, minus 1, 5, minus 35, 285, minus 2,530, 27, 23,751, minus, etc. Okay. Then you search. When you do that, they will list a whole bunch of people who have used these particular coefficients, and I put in the first 4, 6, 8, 9, and they had them going out to whatever number this is, and they have a general solution to it. So each of these sequences it's obviously, since these are all alternating signs. There's a -1 to the end in front for mine, but they're doing it for the positive ones. So theirs is the binomial of 5n over n divided by 4n plus 1. And so we can use that to finish our sum. So we now are ansatz. We don't have to do it for a finite number of terms. We can do it for an infinite number of terms. So -1 to the n, the binomial 5n over n over 4n plus 1, and epsilon to the j. And amazingly, I never expected this. When you sum that, you get a convergent series solution. Unfortunately, the radius of convergence is 256 over 3,125, or about 0.0812. So you would have to have an analytic continuation of the solution to get a correct answer at epsilon equals 1. But it does have a convergent solution, and it can be written in terms of a generalized hypergeometric function here as a function of epsilon. And if you take a look at that solution, if you go for the brown line is the convergence, the radius of convergence, way down. Since the hypergeometric function can be analytically continued, that blue line is the hypergeometric function. And it turns out that the analytic continuation gives you at epsilon equals 1 the right answer. So amazingly, by doing analytic continuation of the hypergeometric function, you can get a solution. That just blows my mind. But suppose we didn't know how to sum the series, or didn't have software that knew how to sum the series, and we didn't know how to do analytic continuation. What could we do? And we're definitely not going to worry about theorem and proof, because what we're going to do is absolutely just amazing that it works at all. Doesn't make any sense to me, but it does. So we'll see. We won't finish this week because, as I said, I got close. But everybody know about pod A approximation? Anybody not know about pod A approximation?
I don't know about it.
Okay. Well, pod A approximants are, quote, best approximations of a function at a specific point by a rational function of a particular order. So you can have a polynomial of degree m divided by a polynomial of degree n, and you can take a particular function and match all the Taylor series of the two, the rational function and the function you're trying to approximate at a particular point, and then match them to be equal, and you'll get a rational function approximation to the function you're trying to approximate. And this was the technique that was originally done by George Frobenius, but he only introduced the ideas and didn't take a look at a whole lot of what was being done. In 1890, Henri Padé, whose image is on the right, did most of the work that is used, and why we call it Padé approximates instead of Frobenius approximates. Now, the Padé approximate, and we're not exactly sure why, usually gives a better approximation of the function that we're trying to get the answer to than the Taylor polynomial, that is truncating its Taylor series, even though we have the same number of coefficients in the two being identical. And it will often work when the Taylor series doesn't converge. And it is the fact that they will work when the Taylor series doesn't converge is the reason why it's going to be important to us to understand it. So we know we have a divergent series, and we want it to be well approximated at epsilon equals 1. And we want to do that by a Padé approximate. Unfortunately, although it will work quite well, which we'll show next week, nobody knows why. It works really well. So we're looking at a lot of material here. This is Abranowitz and Stegun, Foreman Acton, Bateman, Bender and Orzog, Erdle, Magnus, Oberheitinger, and Trichomi, Erdle again, Erdle itself, Frost and Purcell, Gasper and Raman, Carl Friedrich Gauss. This was the original hypergeometric function. Grajdan and Rijik, which everybody had on their library in the 60s, because they were the table of series, integrals and series, and you always had to go and look at everything because nobody knew how to get the solutions. But these two Russians had all of these amazing integrals and series and products in there. Graham, Knuth, and Potashnik did a lot of work on how to design some of these programs for computers. Hardy did divergence series. Luke did a lot of work on special functions and their approximations. The book I started reading was by Rainville in 9th grade, also on perturbation theory, or approximation theory, asymptotic theory, I should say. So here's the initial work done by Meyer, and then everybody, of course, knows Morse and Feshbach, because that was where almost all of the special functions came from when you were doing theoretical physics. And we've been using Strogatz, and of course, one of the major works, which was originally done in 1927, is Whittaker and Watson. which again, in the 60s, everybody had to read that. And then there's Barnes' work on the generalized hypergeometric function. So I'm going to continue this, and I'm going to show you how we're going to use the perturbation theory for the divergent coefficients. And amazingly, it will give us a good approximation to the real solution we're looking for in our second part problem. So that's it for this week. Let me stop the share, change this, go back here, stop the